Okay, let's do the last couple examples here. So, example 8, we have the rank of A is 1. Remember, that means the dimension of the column space of A, and it's equal to the dimension of the row space of A. We showed back in chapter 1 sometime that you can make a basis for the column space of A using pivot columns of A, and you can get a basis for the row space using pivot rows of the reduced echelon form of A. Either way, this number 1 is equal to the number of pivot positions in A. So what can we say? Well, we want to find the dimension of the null space and the dimension of the null space of A transpose. Well, let's see. Maybe we can use this. We have this theorem about dimensions of things. And let's start with the dimension of the null space of A. We know the dimension of the null space plus the dimension of the orthogonal complement of the null space is equal to n, which is the number of entries in the vectors in W. But what is that in this case? Well, if we're talking about the null space of A, how many entries are in null space vectors? Oh, well, here's one. The fact that this vector has 4 entries, and it's clearly in the null space because A times it is equal to 0, means the null space of A is a subspace of R4. So that means the n here is actually 4. So what I want to do is just get this by itself. What can I say about this other thing? Can I figure out what this is? Well, let's look at the 4 related subspaces theorem. This says that the null space is the same thing as the row space of A orthogonal complement. So maybe we can write that over here on the side. So yeah, the null space is the row space of A's orthogonal complement, but I want to have the orthogonal complement of the null space. Well, what if I just take the orthogonal complement of that by theorem 5.7 part 3 here? Those orthogonals are just going to cancel out. The orthogonal complement of the orthogonal complement of the row space is just equal to the row space of A. So yeah, we can substitute this with the row space of A. And do we know what the dimension of the row space of A is? Oh yeah, it's 1. So in other words, the dimension of the null space plus 1 is equal to 4. So the dimension of the null space of A is just equal to 3. Okay, so that's half the problem. Now what about the dimension of the null space of A transpose? Well, we know A is R by 4. A must have 4 columns in order to multiply it by this R4 vector. But how many rows does A have? Don't really have that information. But A transpose is going to be 4 by R, whatever that is. And so the null space of A transpose is going to be a subspace of RR, the reals to the power R, because vectors in this need to be vectors that you can multiply the entries in these vectors by the columns of A transpose for that to make sense. So we can say that the dimension of the null space of A transpose plus the dimension of the null space of A transpose's orthogonal complement adds up to R, but the null spaces of A transposes orthogonal complement, like we just did before, that's going to turn out to just be equal to the column space of A. But we still don't know what R is. We do know that the dimension of the null space of A transpose plus the dimension of the column space is R, but the dimension of the column space is also 1. So yeah, the dimension of the null space of A transpose is R minus 1, but what is R? Is there any way to tell? Well, it turns out there is no way to tell. The example in the textbook I use is if A is this matrix here, this has R equal to 1, and the dimension of the null space of A transpose ends up being 1 minus 1, which is 0. Or A could also be something else that has a bunch of rows. Maybe some of the rows are just zeros. Maybe some of the rows are multiples of this other one. Either way, this still has a single pivot position, so the rank of this matrix is 1. And now R is 3, and this makes the dimension of the null space of A transpose equal to 2. So there's no way to know the dimension of the null space of A transpose just with the information given here. Okay, so let's look at example 9 next. This one's actually going to be maybe a little easier than the previous one. So we want to find the orthogonal complement of W if W is the set of vectors W1, W2, W3 that make this equation true, 7W1 minus W2 equals 2W3. Now, the trick is we can write this as the null space of something because this equation is the same as saying 7W1 minus W2 minus 2W3 equals 0. Or in other words, the matrix with just one row, 7, negative 1, negative 2, multiplied by a W vector is the number 0. So this is the same thing as saying the subspace W is the null space of this matrix 7, negative 1, negative 2. Because that's what a null space is. It's the set of W vectors that you can multiply by that matrix and get the 0 vector out. Now we're going to do the same trick as before using the for subspaces theorem that says the null space of this matrix is equal to the orthogonal complement of the row space. But our goal, remember, is to find W perpendicular. So let's just throw another perpendicular on here. And now the perpendiculars will cancel out. So the orthogonal complement of W is just the row space of this, also known as just the span of the vector 7, negative 1, negative 2. So the for related subspaces theorem to find a relationship between the spans of lists of vectors, as in like the row space and the column space, and relate that with solutions of homogeneous equations. In other words, the null space. So that is that section. Good luck with the exercises. I will see you later.